in English, and then we can do a parallel translation for the discussion. What
Oh,
is better?
no problem. You could, what is it? Giving the presentation in English. We understand, but uh, most of us is passive in English. We could understand what you're saying, but sometimes to give, what is it? The response is still very hard for us, gitu. So I
Yeah,
will translate if there is my student have the question, maybe I will translate it for you. Thank you, Mr.
okay. Thank you so much, Mr. Thema. It's not my first language, so apologies for the accent as well. I can share my screen now. Please let me know if you can see it well.
Okay, you could share screen.
Yeah, do you see it well?
Yeah, we have said.
Okay, great. Thank you so much again. I will be talking today about data science in geochemistry. As Ms. Ramoldi already mentioned, I work as a geodata scientist at Goldspot Discoveries. I completed my PhD at the ETH Zurich a couple of years ago. And today I will talk about first the introduction to the workflows I've been using within the framework of my PhD, and also as a process that I have developed for the open dataset by Scott Haley. I will start by discussing the main principles of using machine learning algorithms and the challenges that we face when working with geochemical data. And I will talk about two case studies. The first one is based on my PhD and is dealing with the interpretation of geochemical composition and multivariate geochemical patterns of zircon with the purpose of extracting the prospecting criteria. The second case study will show the interpretation of an open source data set from the Vizcachitas porphyry copper deposit. This data and the description of that data belongs to Scott Haley and is openly available on his website. And I will show one aspect of how we can take the traditional geochemical interpretation one step further with help of machine learning. Please interrupt me if you have some questions or if you need some comments. I'm open to starting the discussion from any place in the presentation. So first, we can see that over time, the amount of data has increased significantly. On the left-hand side of the slide, you see a plot from a classic Pearson-Gale paper from 1977, which was one of the first ones to discriminate different types of lithologies based on the ratios of trace elements. Zirconium over yttrium and titanium over yttrium is used here to differentiate between plate margin basalts and within plate basalts. And as you can see from the plot, there are not too many data points here. And when the amount of data is small, it's easy to draw the lines on the diagrams and design your rock classification based on whether you visually identify breaks or certain groups within the data. On the right-hand side, you see a plot from Scott Haley's paper from 2020. And this plot contains about 3,000 data points. As most of the properties of the rocks are not always discrete, but sometimes continuous, when we have 3,000 data points, it's very difficult to identify patterns by eye and draw the manual lines for discriminating rock types. And for example, here, if we plotted just the data points, we would not see any trends at all because the entire area of the diagram would be covered by data points overlain onto one another. So in order to see something, we need to use the density contraplots. And only then we can start identifying patterns in the data and devising our own classifications. Like here, Scott Haley uses strontium over yttrium versus yttrium to discriminate the ore-related lithologies from the normal arc lithology types. As I mentioned, there is a huge amount of data now with commercial data sets amounting to sometimes 500,000 data points. Plus, the set of elements that is analyzed is getting bigger with time. And sometimes when we have 50 different elements, it is important to understand what are the purposes of interpretation and what elements could be selected as features, be it for the traditional geochemical interpretation or for the machine learning analysis. And it's difficult to look at the data in 3 dimensions already, and it's impossible for a human eye to discover patterns in the dimensions like 10 or 20 or 50. This is only possible for the machine learning algorithms. But in order to simplify the process, we can use principal component analysis, for example, and see what elements are behaving in a similar pattern. In this paper by Rajic, Molnar, and co-authors, this example shows analysis of the composition of the pyrite from the Raja cobalt gold prospect in the northern Finland. And the data points are colored by the ore associations, and the size shows the content of arsenic in the pyrite. And we see there is a similar behavior of copper and cobalt, for example. Quality of the data is less of an issue now than before, but still, sometimes we have different data points with not all the elements analyzed or present. Many cases show that the elements are below the low detection limit, so there is too little of that element in the sample to be identified by the geochemical methods that are used, or sometimes when we deal with the ore samples, there's too much of certain elements, and then the high detection limit takes place. It's up to every geochemist or geologist to decide what to do with those values. You can choose to drop those rows from your data set and not look at them, or you can use the machine learning algorithm of imputation to fill in the missing values with a certain number that is calculated based on the other elements. Also, one of the challenges is to combine different data sets that has been collected over time, because the analytical methods evolve, the detection limits become lower and lower with time, and what has been below detection limit before 20 years ago now can be analyzed, and anomalies can be extracted from that data. So it's a challenge to combine historical data and modern data. Plus, the closer you get to the detection limit, the more uncertainty there is. And it's also useful to put the number of how sure you are in the different levels of elements that are measured. I will start with the first case study from my PhD. This is the area in Serbia. I had the opportunity to study the Bor porphyry copper deposit, which has probably an analog in Indonesia, Onto. At least in terms of massive sulfide textures, the samples look very similar. It's a porphyry copper system located in Serbia within the Apuseni-Banat-Timok Srednjogorje metallogenic belt, which stretches across Romania, Serbia, and Bulgaria. It's one of the best endowed metallogenic belt in Europe, with many mines still operating today. The Bor mine has been active since 100 years. The results of the workflow of analyzing the composition of zircon is published in the paper by our colleagues. And there is also an appendix to that paper which has the code that we used for processing the zircon geochemistry datasets. The purpose of this workflow was to understand whether we can see the differences between different localities within the Bohr area and whether we can train the machine learning algorithm to identify and fingerprint those localities based on the zircon geochemistry composition. Here I have listed all of them. Bohr and Chukaru are two neighboring deposits, and while Bohr has been active for more than 100 years, its neighbor Chukaru to the south has been discovered only in 2014 because it's been undercover. Then there are localities with a porphyry style mineralization and some localities that don't have a lot of mineralization and are considered barren. Here we look at the ratio of different elements: ytterbium over gadolinium, cerium over samarium, and europium anomaly, and try to see if there are any differences between those locations. And while there are certain groups that we can distinguish from the plots based on their color, we see when we plot the ellipses, every ellipse and its color corresponds to a certain data group. And for some localities, there is one data group. For example, Vallestrž and Redan Krepolin, these are the barren localities, showed in gray, while for the other deposits, there are several subgroups within the data groups. And we see that many of them overlap. Plus, we also see that the traditional Europium anomaly criterion that is used for the exploration in porphyry copper systems doesn't seem to work in our area, because usually people look at the Europium anomaly within zircon and say that the cutoff of 0.3 can be used for separating mineralized rocks from barren rocks, or mineralized source lithology from barren source lithology. However, in Timok area, everything seems to be above 0.3, which means that the traditional exploration criteria is not working for us. And we have to look for something different, which can help us to address the source lithologies for porphyry copper systems with more certainty. The workflow that we used was first to select the training data. And as training data, we used the trace element composition of zircons and also calculated cerium in Europium anomalies. We took the entire data set with about 1,000 data points. Then we performed scaling because machine learning algorithms are struggling to deal with the natural data. Usually, if you want your machine learning algorithm to perform very well, you would want your data to be normally distributed. However, in geochemistry, nothing is normally distributed. We have multi-nodal peaks of distributions. We have sometimes randomly distributed variables. So using the scaler helps to bring the distribution a little bit closer to normal, although no matter what kind of normalization or scaling algorithm you use for geochemical data, it's rarely possible to achieve the classic normal distribution shape. So we use the geochemistry of the zircon as the input training data, and then we take the labels, which will be our target variable. In this case, it's the name of the deposit or locality, and then we try to solve the classification problem. That is, take the geochemical data as an input, take the name of the locality as the target variable, perform the train test split with the stratification. Stratification is a strategy to make sure that all the classes, in our case, the names of the localities, are present in similar amounts in the training and in the test set. For example, if we only have 200 samples from a certain deposit, When splitting the dataset into the train and test subsample, we make sure that 70% of those 200 samples go into the training set and 30% from that deposit go into the test set. So there are no surprises, like, for example, if we performed completely random splitting, we would have possibly a situation when samples from one of the localities could go only into the test set. So the machine learning model would not see those samples during the training stage, and therefore it would not perform well on a test sample. After we have split our dataset into the train and test set, we tune the parameters, and then we let the model learn. And after the model has finished learning, we perform predictions and the evaluation on a test set. There are two main metrics that we look at, and the classification report, which is generated automatically with our code, shows how well the model has performed on each class. Finally, we want to evaluate the results not only from the accuracy point of view, but also from the viewpoint of the importance of input variables. For that, we use sharp values, which show what geochemical parameters were most important for the model to predict the location where the zircon is coming from. Here are the results of the predictions. The predictions are evaluated on the test set. That's why the number of the samples is quite small. And we could see that the model could guess the locality where the zircon is coming from with accuracy of 89%, which is pretty good. As we usually deal with imbalanced datasets, we can use the techniques that artificially augment our dataset to make it balanced. But even when we use those techniques, we still see that it's always good to have a large number of samples. So we see that the confusion matrix, and I will explain a little bit what this confusion matrix means. Ideally, when we look at the confusion matrix, we want to be on the diagonal. On the x-axis, we see what samples were predicted in what classes, and on the y-axis, we see the true labels. So every point in the test dataset is analyzed from the viewpoint, what locality did the model think it is from, and what locality it actually is. And when we see that those localities coincide, we say that the model has performed well. That's why on the diagonal, the predicted label, for example, bore, coincides with the true label. So the zircon is actually coming from bore, and the model thought it's coming from bore. So on the diagonal are all the samples that were predicted correctly. We also look at the values of the diagonal to understand what model was mostly confused about. And I would like to focus your attention on the bottom row of the left confusion matrix. For example, you see that 7 samples coming from Majdanpek were predicted as Majdanpek, but actually they come from Veliki Kriveli deposit. It's the bottom row, third cell from the left, which is remarkable because those localities are very close to each other. So even when the model is wrong, it's wrong in a way that we can explain. And those are also very valuable results when you're looking, for example, at core logging and different labels that are misclassified. As I mentioned before, it's important to know what input variables were most important for the model. And here we compare two different classifiers and see that barium, phosphor, and cerium were equally among the first three most important variables for both models. It's also a good way of evaluating the predictions by comparing different models, more than two, and seeing what are the similarities. Because if several models are thinking along the same way, there is a higher chance that they actually are right and predict the realistic properties of the geological system. So here we see the importance of different variables for different classes. The legend explains what localities, Bor, Maidenpec, Nikolichevo, and so on, and the size of the bar on the feature importance plot shows the importance of that feature, split into different localities. So here we conclude that in order to predict whether the zircon is coming from an active copper deposit or from a locality that doesn't have a lot of mineralization, it's important to focus on barium, phosphorus, and cerium in the first place. Uranium, thorium, niobium, and europium anomalies and cerium anomalies are also important, but as opposed to using only a single criteria of europium anomaly of being 0.3, we prefer to use a combination of geochemical criteria. And as we see, europium anomaly is used as the first filter traditionally, but for our models, it ended up being only the ninth most important variable. So as a conclusion to the first case study, I will stress again that machine learning methods are helping humans to interpret geochemical patterns because machine learning algorithms can see in many directions and many dimensions, while a human eye is limited to the interpretation of the 2D or 3D plots. The best model that has been successful for this case study was random forest, and it could predict the locality with the accuracy of 89%. Both europium and cerium anomalies had an effect on the model results, but barium, phosphorus, cerium, and hafnium were more important than europium and cerium anomalies. There is always a potential for improvement, and more data being collected by different research groups, and it's always good to have a larger and more balanced data set. Then, once we have predicted the localities, we can proceed to all the other types of predictions. It doesn't matter what kind of categorical label you're trying to predict. You can always redesign your classification, add new data, adjust the model, and see if it's still performing well with new data. I will continue to the next case study. At the bottom of the slide, you see the link to the open source tutorials from Scott Haley website. He usually does the geochemical interpretation with the help of IOGAS software, and he has very good explanations. For example, in this case, how to define alteration styles based on potassium to aluminum plots versus sodium over aluminum, and on the ternary of potassium, aluminum, and magnesium. So he describes in detail the workflow where you manually draw the polygons on the diagram and assign different alteration styles to the data points that are within that cloud. On the left-hand side diagram, you see on the top there is a K-feldspar. On the right, of the diagram at the bottom, there is albite, and then you have muscovite, cordierite. So you can draw your polygons and assign the classes of alteration, like adelaria, illite, chlorite, and so on, and then check the assignment against the ternary diagram. So what we can do in addition to this, we can check the correlation between different elements and see if our geochemical interpretation is actually holding together when we apply numerical methods. This is a correlation diagram, which is filtered for all the values above 0.5. We can have a long discussions about what is significant, but generally we could say that everything above 0.7 shows that there is a significant correlation between the variables. What is remarkable here is if you look at aluminum, you see that other immobile elements like zirconium, titanium, niobium are largely correlated with aluminum, which shows that for this data set, the assumption that all the immobile elements follow similar patterns is true. What you can also do with the geochemical data and categorical data, like in our case, different alteration styles, you can split your ore into different domains. In this case, silver is used as the variable to calculate the progressive half. Inside that circle and on the left-hand side of the diagram, you see that the dark blue is related to all the samples that have silver below the median. Everything in this data set, the median is at 0.42 ppm of silver, is marked as the first half. And then progressively, as you go higher in concentrations, you split your data set into different classes. So from blue with the low silver values to bright pink, which is the highest silver values. And when we compare the data on mineralization and alteration, we can see that most of these samples with low level of silver belong to the chloride group or least altered group of samples, or to illite, chlorite, and albite. It's useful to look at those two plots in combination and see the magnitude of the flows between the ore samples and the alteration classes. And as we go higher in terms of silver content, we see that chloride and least altered classes become smaller and virtually disappear for the high-grade samples. And classes like adelaria, illite become more important, which can allow us to make conclusions about alteration styles and how important those alteration styles are for silver mineralization. And then again, to avoid the objectivity of a human interpretation, we use those variables to try to predict the alteration labels in a completely automatic manner. And our results show that we achieve accuracy of about 80 to 83% with different classifiers. So in this case, the assumption that alteration can be related to mineralization is also true. Going back to the feature importance plots, we look at different classifiers and we can use our geochemical expertise to understand whether the machine learning model is thinking in the same way as the human geochemist does. Random Forest has decided that sodium, potassium, tellurium and barium are the most important variables. But in reality, when a human geochemist is interpreting the data set and decides on the alteration styles, it's using exactly those 4 elements that another classifier has thought important. So if we go back to the 2D and 3 and ternary plot that we used before, we see that potassium, sodium, magnesium, and aluminum were thought to be the most important features by the CatBoost classifier. And if we go to the beginning, where we had the human interpretation of alteration styles, we see that these are exactly the same elements that were plotted on the diagrams on the ternary between aluminum, potassium, and magnesium, and on the molar ratios of potassium over aluminum and sodium over aluminum. So in conclusion, I would like to stress again that progressive half, the way of plotting all your samples in terms of the ore content, is a simple and visually comfortable way of relating alteration styles to mineralization. And the classifier CatBoost has sort of intuitively guessed the variables that a human geochemist used for the assignment of the alteration labels. And it could use those variables to predict the alteration styles based on geochemistry with the accuracy of 83%. I would like to thank you again for the invitation. I really appreciate the opportunity to talk to you about geochemistry and machine learning. And in the concluding slides, I put some links to the examples and sources that you can use for learning more about geochemistry and machine learning. The first one is open source datasets by Scott Haley with the tutorials, which you can download, import into QGIS, and use for building your own workflow and interpretation. The second is a very good GitHub repository by Richard Scott with a lot of links to different resources in the field of not only geochemistry and machine learning, but also geophysics, remote sensing, hyperspectral, pretty much everything. The third one is my GitHub with some of the geochemical workflows, including those I showed today. And then you probably already know, but it's always good to go back to the basics. There are 2 great resources with OpenTalks, GeoHug, and Ore Deposits Hub, which was a really good starting point for me to go and discuss with these experts and to learn about machine learning and geochemistry. So I will stop sharing here. Thank you so much again. It was a pleasure, and I will be happy to hear your comments and answer your questions.
Okay, thank you, Ms. Dina, for the presentation and explanation of data science in geochemistry. It was very engaging presentation. That's so great. That compared to case studies of data science application. So I make conclusion. We have 2 examples of applied data science in geochemistry. The first one model is a tree-based model, which is apa sih namanya, supervised machine learning, right? And the other case is clustering based, which is unsupervised machine learning. Maybe I will combine with bahasa, Ms. Dina, to conclude this conclusion to my undergrad student. Jadi Ms. Dina ini memberikan contoh 2 model machine learning, di mana yang satu adalah tree based yang berbasis pohon, tadi ada random forest dan lain sebagainya, dan ada juga model yang kedua itu clustering based. Clustering based kita mengklasterisasikan dari data-data biokimia yang kita punya, biasanya seperti itu. We can differentiate and study the differences between the 2 model and also compare the effectiveness. Before the conclusion with Ms. Dina presentation, the TRIS model have 89% right, Miss, about the accuracy. Yes, 89% for the accuracy, and the second base model for clustering, the accuracy is 83% model. So in these two models, we can see for the first model, the tree-based model is more effective than the second model. But it depends on the data and the concept of the geology. I think that is the conclusion about Ms. Dina.
Yes, thank you, Mr. Daniel, for the effective summary of the presentation. I agree that there are different factors in how successful the machine learning model is. And we can discuss the differences between the supervised and unsupervised approach. In one of the GitHub repositories, I showed the application of completely unsupervised model clustering and agglomerative clustering to understand the hornblende and magnetite fractionation trend. And there is always a difficulty in understanding how well the unsupervised model performs because you don't have any truth to compare it to. You can predict different classes within the data in a completely unsupervised manner based on, as you mentioned, density-based clustering, for example. And then you can visualize and see whether it makes sense in 3D, or you can make down log plots, but you will never be able to put a number on it because there is no accuracy calculated for unsupervised methods. While with supervised methods, you have the ground truth. In our case, it's either the locality of the zircon or the alteration label that has been placed by the human geochemist.
Okay, great conclusion, Miss. I will teach for my undergraduate student first. Jadi ada dua tadi model supervised machine learning. Ada dua model supervised sama unsupervised. Jadi kalau yang supervised machine learning itu dia menggunakan label untuk menentukan perhitungan antara satu dengan variabel lainnya. Jadi seperti berbentuk pohon, konsepnya seperti itu. Jadi ada beberapa variabel, beberapa komponen kimia kimianya, geokimianya, terus kemudian dia membandingkan satu dengan yang lain, kemudian membuat model. Itu yang supervise. Jadi ada yang mensupervisi, jadi ada labelnya, yang seperti itu. Sedangkan kalau yang supervised machine learning, dia tidak ada labelnya. Jadi tidak ada yang mensupervisi. Ya cuma dikelompokkan masing-masing. Oh yang ini berdasarkan kesamaan tingkat ppm-nya. Oh yang ini berdasarkan tingkat kesamaan warnanya. Oh yang ini berdasarkan tingkat kesamaan apanya. Yang seperti itu. Itu bedanya antara supervised and unsupervised machine learning. The difference that supervised machine learning and unsupervised machine learning. Okay, now we are moving on the next section, which is the Q&A section, question and answer. Please feel free to ask any question you might have to Miss Dina. Monggo silakan teman-teman kalau ada pertanyaan. Are there any question? Mr. Tema. Monggo.
Okay, thank you, Miss Tina, for your presentation. It's very interesting for us. I would like to asking for you when we face like your data. There are so many data. I think I'm so confused when see how could we conclude if we have like various data something like that, and you know this is very interesting for us because machine learning could make it more simple to give us to consider maybe decided to how the conclusion of the data say to us. As a geologist, we will also learn about it. And my question is, uh, if we change the equation, or maybe if we change about the purpose of the machine learning, could the what is it? Could the significancy change at there, Miss Dina? Jadi maksudnya anu Mas Daniel, kalau kita mengganti apa namanya, formulanya apakah bisa, apa namanya, berubah signifikansinya gitu Mas Daniel?
Oke.
Thank you very much for the
Uh,
question, Sama.
Yeah, thank you, Dina.
Yeah, I would also like to join you in expressing the opinion that the data sets are we work in the data rich environment. And sometimes it's a bit overwhelming to deal with so many variables. But as I mentioned, we can compress it in the form of principal components, for example. And the advantage of principal components is that you raised the very important point about looking at the equations. Not all the machine learning models allow you to do that. Some of them are purely black box, where you have the input and you have the output. That's why choosing simple methods, which you can still express in terms of equations that are understood by geologists, is very beneficial. Principal components is actually a linear combination of input variables. So when you look at the principal component, they are ranked in terms of how they explain the variability of the dataset. And they also have a direct connection to the input variables. For example, when you calculate principal component 1 for one dataset, you usually see the coefficients and you say like, my principal component 1 is arsenic content multiplied by 0.1 plus gold content multiplied by 0.5 minus silver content multiplied by 0 point something. And this is a equation expression of the principal component. And those coefficients, 0.5 minus 0.3, whatever it is, allow you to actually link back to your input variables and say that these are the elements that take part in building this principal component. So you sort of keep your like feet on the ground. And also when we talk about classifiers, decision tree, the simplest of them all, is very useful because then you can visualize it in form of the different branches and steps you take. A very straightforward example is, for example, looking at strontium and yttrium for the porphyry copper deposits. The first step would be to look at the strontium content and say everything that is above 30 has a potential for being prospective. Everything that is below 30 has less potential. And then you make that step and look at the remaining data with strontium content above 30 and say, now we look at yttrium. Yttrium below 0.5 something is prospective. Yttrium above that value is non-prospective. So you can actually move along all the steps of that decision tree and follow the logic of the machine learning model. And you can even use that as writing the simple Excel statement that will perform the same thing based on if-else formulations as the decision tree does.
That's it, Mr. Tema.
Okay, thank you, Miss Dina. It's very good explanation. Maybe in the next, in the future, I will try with the machine learning for my PhD research, Miss Dina. But the applied is in engineering geology, especially in natural hazard. Because I will take my PhD maybe in natural hazard, something like that. So okay, Mr. Daniel, you could continue your explanation or your question.
Okay, I think we'll add additional information. Miss Nina, can we use principal component analysis or PCA to reduce the variable, something like that, to make effective filters for our model?
Thank you, Ms. Daniel. Yes, I think PCA is the very efficient method of reducing the complexity down to several principal components. For example, in geochemistry, when you have the starting number of variables equals to 54, it's very difficult to visualize them all. So you prefer to compress them into principal components. Initially, the number of principal components can be equal to the number of variables, but then you can start selecting them or filtering them based on what you see makes sense for your data set or not. And also in geology, sometimes classically you would select the first several principal components that explain 90% of the variability or 99% of the variability of the data set. However, in geology and in geochemistry, it's not always that simple because we're looking for very subtle patterns in the data. If we analyze a large area with a lot of samples, and most of them don't have any mineralization, like when we are targeting on a large area and try to find the mineral deposit, which is a bit of a needle in a haystack. So if we use the classic approach and only looked at the first 10 most important principal components, most likely those components would not have anything to do with the mineralization. However, when you start looking at the certain elements that are important, pathfinders, or elements, or alteration-related elements, you see that they're probably not as high in terms of ranking the principal component, but they are the ones who help you finding that little needle in a haystack. However, I think in engineering geology, you don't have that problem, because if you look at the cloud of data related to some mechanical properties of the rocks or the slope stability, you can be safe with looking at the first 10 principal components, because those are the most important and influential properties of your data set.
Okay, great. Thanks, Miss Dina. I will explain in bahasa first for my undergrad student. Jadi tadi pembahasan dari Pak Tema dan juga Miss Dina itu bagaimana kalau misalnya datanya sangat banyak dan bingung untuk memilih. Nah, itu sebenarnya ada satu istilahnya model machine learning, bukan model ya, lebih ke arah reduksi data, reduksi dari variabel-variabel yang kita gunakan. Nama codingannya itu namanya Principal Component Analysis atau PCA. Nah, kita memilih komponen-komponen variabel tertentu yang benar-benar kita fokuskan sehingga kita bisa menggunakan model tersebut lebih efektif lagi. Jadi kita bisa mereduksi. Tapi ini efektif untuk yang datanya sangat big data, yang sangat banyak. Kalau untuk geologi kan tidak sebanyak data umum seperti data-data sosial dan lain sebagainya. Masih ya relatively masih bisa dihandle lah dalam konsep machine learning-nya seperti itu. Jadi kalaupun juga menggunakan PCA itu juga tidak apa-apa. Cuma data kita masih lebih gampang dihandle, kurang lebih seperti itu. Oke. Are there any question? Monggo silakan dari beberapa mahasiswa, silakan bertanya.
Untuk
beberapa
mahasiswa mungkin bisa menggunakan bahasa Indonesia saja untuk bertanya, nanti biar ditranslate sama Pak Daniel atau saya gitu.
Boleh, monggo silakan.
You could use bahasa to ask the question.
Yeah, I would be interested to know what you work with in terms of what student projects are there in the or deposits field? Do you look for applying machine learning in your, I don't know if it's called master's project or diploma project or bachelor project?
Okay, Miss Dina, I think in our message we have one question from Miss Naspuria. Your present is very interesting. How hard we should interpret for geology model in data science? Do you have any advice for newbie user in data science? Maybe do you have advice to how could we start it to learning about data science? Something like that, Miss Dina.
Thank you very much for the question. I think, Gita, hello, nice to meet you. It's very important to use the tools that are available now, because when you start coding, there are all these small things that make the process slower. For example, I would spend a lot of time looking for different commas or brackets in the code that would break the code. But now we have so many good resources, including ChatGPT. And ChatGPT is great for editing your code and asking it to explain things in simple terms. So there are also lots of open source courses that you can follow. And there are so many resources on Kaggle and on YouTube that you can just sign up for a certain free course and start coding. So my personal advice is just start doing it, look at the data, think of the clear goal, what you want the machine learning algorithm to do, and why. Like, ask yourself 5 why questions and understand the question well, understand the answer you're looking for, and think of the machine learning and data science as just a simple tool that helps you understanding the geological system better. And there are many resources in that respect. So you can summarize papers with machine learning algorithms. You can query literature with machine learning algorithms. You can test your hypothesis. You can ask ChatGPT to give you positive and negative confirmation of a certain hypothesis. But you should always keep your feet on the ground in terms of sticking to your own expertise and insights, because at the current state of machine learning algorithms, they are all only as useful as the human interpretation and the answer they can give to your geological question. If you like, you can reach out to me and I'll send you links to the beginner courses for like more technical things like coding and data science. Because right now there is really a lot of resources out there. You just need to spend some time on learning it, and hopefully it will be useful for you.
Okay, thank you, Miss Dina, for the answer. Ya, jadi ditawarkan ada semacam pelatihan yang secara umum ya, atau teman-teman juga bisa mencoba menggunakan ChatGPT, dan mungkin juga teman-teman juga bisa mengambil mata kuliah data science, science data geologi. Kita berkembang lah di sini, kita sama-sama belajar untuk berkembang untuk meningkatkan konsep data science di dunia geologi. I think one last question for Mr. Dina. Once an effective machine learning model has been developed, Miss, can it deploy on a map in the form of spatial data, Miss?
Sorry, could you repeat that question? Once the model is deployed, once the model is trained, can it be deployed?
Once effective machine learning model, if we have one model like random forest model is the most effective, can it be deployed on a map in the form of spatial data?
Yeah, I think you can and should deploy the model based on the spatial data. It's important that you have trained the model with the same variables as you are deploying the model with. And it's important to model the performance of the model, because there are all kinds of possibilities there in terms of the model drift. Sometimes when you perform drilling on the deposit or a new locality, you add new data. And for example, you have drilled lithologies that you have not seen before. And then the model, because it has not been learning on that type of data, it will perform poorly, especially when you get into the area that consists of entirely unknown rock types. So retraining, modeling the performance of the model, adjusting it when needed is very important. It's like monitoring the health of the model, and you can build your own dashboards that show you on the graph how well the model has been performing. And when you see that the performance declines, you can understand that it's time to go back to your original data, retrain the model, and see what you can improve. Also, you mentioned, Mr. Daniel, the spatial coordinates. There are many techniques that allow you to interpret spatial coordinates as variables. And it's a like purest form of connecting to the location of the sample and seeing what influences the whether the location of the sample is a valuable feature in itself, which sometimes happens.
Okay, thank you, Miss. Great answer. I plan to use machine learning data science in field of geological engineering, like geotechnical and engineering geology for my dissertation. I hope I can catch up and make data science in geology, especially in Indonesia, to more brighter again. Thank you, Miss Dina. I think enough for the session question and answer. I will give back to Ramoldi for the Master of Ceremony. Thank you, Miss Dina.
Thank you so much.
Well, finally we have reached the end of this event. We hope that all the materials presented can be useful and can be applied someday. Before closing, there will be a documentation session or group photo by screenshotting. For this reason, all participants are expected to activate their cameras. Mungkin buat sebagai penutup ya, kita bisa dokumentasi dulu. Oke. Okay. Thank you, Mrs. Dina. I'm Moldy as the host of this event. Take my leave, apologize for any mistake in words and deed, and I thank the participant of the public lecture on geological data science for their attendance. To the moderator, Mr. Daniel Raditya, and guest speaker, Mrs. Dina Clemencia, I thank you for your time and useful knowledge. See you again. See you next time. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Waalaikumsalam.
Waalaikumsalam.
Thank you, Miss
Thank you, Miss
Dina.
Dina.
Thank
We
you so
will.
much, Ramon. Thank you so much, Mr. Daniel. Thank you so much, Mr. Thema. It was a pleasure meeting you all, and I wish you good luck with your doctoral thesis, master thesis,
Amen.
and with the application of the machine
Amin.
learning geology problems. Thank you so much.
Thank you, Miss Dina. See you.
Thank you, Miss Dina. See you again.
Yeah, I will
See you.
end this meeting.
Yeah.